Hello and welcome to another video on the first 5 questions from the MAT 2012. So obviously the first 5 short questions tend to be the easier ones. It tends to go from easier to harder, and so I'm hoping that most of these you have not found too bad, but nonetheless, I mean, it is the MAT, so it is going to be pretty tricky. Okay, firstly, nice friendly start this. Which of the following lines is a tangent to a circle with equation x squared plus y squared is 4? Now, you know, if they'd ask you to find the equation of a tangent to a circle, I guess you'd be a bit happier because at least you know which point you're dealing with. And we don't have that luxury here. So all we really know, I guess, is that it's a circle, radius 2, centre the origin. And so it's going to go through 2, 2, minus 2 and minus 2. And you certainly want to be aware of those facts if you're taking the MAT. Now, I guess what I did was I immediately ruled things out. I thought, well, it's not going to be this one because this one goes through 2 and 2, and so it's not a tangent because it actually slices off a segment of the circle. So it's definitely not that one. So I was like, no, it's not that. And then I looked at some others. X equals root 2. I thought, not a chance. Root 2 is about 1.414, so it's not that one. And so I was left with these two, root 2 minus x and x minus 2 root 2. And I thought, well, I can't remember which one I looked at next. Let's say we look at this one, because I'm pretty sure this one isn't the answer, judging at my notes. If you did this one, you'd be like, okay, it goes through root 2 on the y-intercept, which is like there, and it's got a gradient of minus 1, so it's definitely not that one. So by a process of elimination, it must be B. But I actually didn't get to the answer like that. I think I looked at this one and thought, well, it's going to hit at minus 2 root 2, which seems a bit more like it, because that's about minus 2.828, because root 2 is 1.414. I've often found that knowing that, you know, 2 or 3 decimal places is actually quite handy. This is 2 root 2, minus 2 root 2, so it's minus 2.828. This is just the only one which it could be, really. But I also knew this has got a gradient, oh, hang on, yeah, this has got a gradient of 1 as well, so I'm trying to draw it with what looks like a gradient of 1. And so if it's got a gradient of 1, that's going to be 2 root 2 as well, isn't it, up here? And I just thought, well, that does actually make sense being tangent, because it would then be at right angles to this bit, and therefore if that's 2 root 2, and this is an isosceles right angled triangle, well, that only makes sense if that's 2, and that's the radius, isn't it? And that gap's 2, which looks right. So it makes a lot of sense, yeah? That's what will give you that side of your triangle being 2 root 2. But there we go, you can do it by process of elimination, really, I guess. But yeah, there we go, that's the first one. So the first answer is B. Next one, okay. Let n equal 2 to the k times 4 to the m times 8 to the n. Then n will definitely be a square number whenever. Okay, so first things with this is quite naturally to turn them all into powers of 2. So you've got 2 to the k times 2 to the 2m times 2 to the 3n. That makes sense, doesn't it? And that gives us n is 2 to the power of k plus 2m plus 3n, if we just apply the rules for powers. Now, we want n to be a square number, yeah? So in other words, we want this to be like some other number m, where m squared equals 2 to the k plus 2m plus 3n, yeah? Now, I suppose the easiest way to look at it is like with powers of 2, yeah? Powers of 2 are only square if they're even powers of 2. We need the power of 2 to be even, yeah? So we need k plus 2m plus 3n must be even, yeah? Because only even powers of 2 are square. Look at it, 2 squared is 4, 2 to the power of 4 is 16. Those are all squares because they're something squared. Whereas the odd powers of 2 are not square numbers. Look at 8, yeah, most obvious example. So k plus 2m plus 3n must be even, and hence, now if k plus 2m plus 3n must be even, well, you could easily rewrite this as k plus 2m plus 2n plus n, yeah, and this middle term is definitely even, isn't it? And as that's definitely even, we need k plus n to be even as well, and therefore the answer is D. There we go. So not too bad. Okay, I really like these kinds of questions. These, what is the smallest of the following numbers? There's lots of ways of doing it. normally. I personally wrote this as 3 root 3, and I actually even estimated it. I'm not sure my estimation was particularly useful in the end, I can't remember. But this is 3 root 3. Root 3 is about 1.7, so times it by 3, it's roughly equal to 5.1. And if they're very close, you won't get away with these estimations, but it might not be that close. Log base 3 of 9 squared is really log base 3 of 81. And log base 3 of 81 is, what do we need to put 3 to the power to get to 81? It's 4. Now, sine of pi over 3 is sine of 60 degrees in old money, if you like. So that's root 3 over 2. So this is 3 root 3 over 2 squared. And 3 root 3 squared is going to be 9 times 3, which is 27 over 4. Yeah? Worth writing down. Oh yeah, we're looking for the smallest, so immediately I can exclude this one, because this one beats it. This is about like, what is that? Just do it in my head for a second. That's going to be 6.75, isn't it? So that's no good. I think I've written it down in my notes as 6.25. Wow. Yeah, 27 divided by 4 is in fact 6.75. I was looking down at my notes and I was thinking that doesn't make sense in my head. Shows, you know, we all make mistakes. But anyway, needless to say, it's not as small as 4. And then what we got here? Log base 2 of log base 2 of 8 to the 5. Well, that's the same as log base 2 of log base 2 of, now 8 is 2 cubed to the 5, multiply the powers and you're going to get 2 to the 15. And so we're really doing log base 2 of, what, log base 2 of 2 to the 15, well that's just 15, yeah? Now I just estimated this, and I had estimated this as just under 4, because 2 to the power 4 would give me 16 here, and hence D is the smallest one. Done. Okay, D. Shown below is a diagram of the square with vertices 0, 0, 0, 1, 1, 1 and 1, 0 and the line y equals x plus c, and this shaded region which lies below the line y equals x plus c is an area A. Yeah, it's just the area of this square. And they want to know which of the following graphs shows A, the area, as C moves, yeah, as C varies. Well, as C gets bigger and bigger and bigger and goes from -1/2 up to 1/2, because I mean, well, actually down here, you think about it, down here, can I draw on this? Oh, it's going to mess up. Let me just do it by freehand then. When it's like first coming up to here, that's going to be at like -1, -1.5 or something like that. -1 actually is where it's going to start, isn't it? Because it's got a gradient of 1 this line, and we want it to have 1 on the x-axis. Well, that's the line y equals x plus 1, isn't it? Like when x is 0, sorry, x minus 1. What is happening with me today? Yeah, that's going to be the equation of that line when it just hits 1. And so it's going to start at -1c, and it's going to travel up to like 1. And that's what should be happening on these graphs down here. Now, I immediately excluded most of these. In fact, I went straight for the answer just by kind of common sense. I thought it well, firstly, it's not going to be wavy like that. Like, that doesn't really make any sense, because surely the area is going to increase all the way across. It's always going to be increasing. Okay, they all show increasing area. But if you think about it, there's going to be a critical value halfway through when C is 0, yeah? And that's going to be like an inflection point. And that's why immediately I was thinking it's A. It's going to inflect them, because think of how the area changes as this moves across, as C varies, yeah? Like, the area must be like a gradually increasing function initially, yeah? Because when you move from there to there, say, you get a little bit of area. But when you move the same distance, when you vary C by the same amount, can you see that that area is a lot larger than that little area? And that's why it needs to be growing up to the point where you get C is 0. And then, because the area is not filling up so much, it will be slowing down in terms of how big the area comes from. And that's why the answer is going to be A here. I've literally just written down A by inspection here for my working, which means, like, you know, I've just kind of worked out in my head. I thought it's not constantly growing the area. That would only be the case if you had like this kind of situation with a line straight across it and the line was lifting up. It doesn't work like that on a diagonal of a square, because as you go across, it's a terrible diagram. As you go across, I'm trying to draw straight lines here, but I'm really struggling. As you move C by a constant amount, the area gets a lot bigger than a constant amount. It's growing faster and then slower again. And I can just kind of see that. I don't know if that's a very good explanation, but that's how I did it nonetheless. Now E I quite like, because I mean, firstly you've got 2 points stationary, sorry, you've got 2 repeated roots there, where the gradient is 0, so we certainly need ones with 2 repeated roots. Now some of these don't have 2 repeated roots. Now for example, this one does, because that's x squared minus 1 is actually the same as x plus 1 x minus 1, and so and it's been squared, so x plus 1 is squared and x minus 1 is squared, so this one's still in play. This one though, yeah, okay, this one has x equals 2 and x equals minus 2, so this one's still in play. This one doesn't, so I can get rid of b straight away, and I like these ones where I can eliminate possibilities, but no, because it does not have, I suppose it could be positive root 3 and negative root 3, yeah. Notice as well, I suppose I should have checked first, but it does look like a quintic. It's certainly looking like that anyway. A quintic has up to 4 turning points, 1, 2, 3, 4, and that's exactly what we've got here, 1, 2, 3, 4. But I think they are all quintic, aren't they? X squared, x, yeah. So this one is still in play. I apologise, because you can factorise the x squared minus 3 into x plus root 3, x minus root 3. And what about the top one? Yeah, you could have x is 3 or minus 3 there. So in the end, anyway, I'll tell you how I did it. I was trying to eliminate one there, but I absolutely failed. I suppose one thing which is worth saying is it's a negative x to the 5 graph, because generally speaking, cubics, when they're positive, look like that, and so do quintics. When they're positive, they look like that. When they're negative, they go the other way around. So it must be a minus x to the 5 one. Now that rules out a, because after you square that minus x, you're going to get positive x squared. Oh no, it doesn't rule out a. I keep trying to rule things out, but no, it doesn't rule out that one. But it must rule out some of the others, because it doesn't rule out b. That's going to be minus x to the 5. It rules out c. Definitely can't be that. And it doesn't rule out d. So we've only ruled out c so far. Okay, I suppose we better note now that this has got 3 roots. Yeah, 3 places where it touches the x, where it touches or crosses the x-axis. 2 repeated. Yeah. So let's try and make sure our quintic has 3 roots and 2 repeated. Okay, that's going to have 1 repeated root, 1 repeated root, and x equals 1. But if you look, that's going to be like 3 minus 3 and 1. Well, that doesn't really make any sense, because our repeated roots are at 3 and minus 3 here. Yeah, and our non-repeated root, our intersection, is at 1. Well, it doesn't make sense for that to be minus 3, that to be 3, and that to be 1. So a is out of there. We've eliminated a as well now. Good. So we've only got b or d to go. Now, I suppose this one, if we think about the roots, you're going to have root 3 and minus root 3 as possible roots. But the trouble with this one is that those aren't repeated roots. Oh, excuse me. So I should have eliminated earlier, because they're not repeated roots, and you need 2 repeated roots. Now the answer is D, because look at this. You've got x plus 1 squared, x minus 1 squared, 3 minus x. That makes sense for that to be at minus 1, that to be at 1, and that to be at 3. It can't be any of the others. It just doesn't make sense for it to be any of the others. These just don't make sense, because you'd have minus 3, 3 and 1, so it must be, the answer must be D. Is that what I got in my notes? Let's have a look. Yep, D by inspection. Cool. So I hope that made a bit more sense out of that. I suppose this one's the weirdest one, but just think about, as you move this, shift this by a constant amount up, the area increases by a non-linear amount. That's the thing. Just think about, like, you know, how the area goes up a lot more. Like I say, if you keep the gap constant between this one and this one, where you can see that the area is increased by a lot more. And so it has to be one which is growing like that, and then slowing down as it does the opposite at this end, because it will slow down how much area it's, you know, like assuming. You could actually, thinking about this, you could probably work out exactly what the area change is. I don't know if I've ever done it like this before, but let's think about what this area would actually be. This distance is always going to be, in terms of c, this is going to be 1 minus c, isn't it? Let's say c was at like minus a quarter down there, like, then that would be 0.25, wouldn't it? Because you'd be dealing with y equals x minus a quarter, and therefore that would also be 0.25, in which case this distance would be 1 minus c. And by symmetry, I can say that's going to be 1 minus c. And therefore the area of c is going to be 1 minus c squared over 2. Yeah. Now, this is a graph of a of c on the y-axis and c on the x-axis. Yeah. And so we can see it's got to have some kind of a quadratic curve. And by the way, this only works up until you get up to here. Yeah. So it must look initially from -1 up to 0 like a quadratic, just like this one does. And what's more, it's a right way up quadratic, because that's really c squared minus 2c plus 1 over 2. Yeah, so it looks like a right way up quadratic up to there. And then when you get to this side of it, well, you're going to have to work out the area differently then, because you're going to have like an area of a half plus, and then you're going to be adding on like this bit, like, which is like, and this is, I'm going to try and work out the whole area for you, but I hope you can see now it's definitely going to be this one, because that's the only one which looks from -1 up to 0, like it's, you know, the bottom half of 1 minus c squared over 2, which has a root at, you know, -1, a repeated root as well. It just looks so right now. But yeah, if you were doing it the other side, well, you'd have after c equals 0, you know, well, basically for c is greater than or equal to 0, you're going to have the area of c equals a half plus, because I'll just add on, that's half the area of a 1 by 1 square, so that's going to be all of that accounted for. And then to add on this extra bit here, well, why don't we do like, it'll be probably easier for us to work out the area of this, which is going to be, because we know that's the value of c now, because this will be where the line is, you're going to do 1 minus c times 1 minus c over 2. Yeah, you're going to do that again, but that's for the missing area. So if you like, it's going to be a half minus that, which we need to add on. So we've got a half plus a half minus 1 minus c squared over 2. And so that gives me 1 minus c squared over 2. And I think that's the case when c is greater or equal to 0. And can you see that's going to be a negative quadratic, which looks something like that until you get up to 1, where, you know, clearly the function, you know, the model of the function fails. But that's why they get that graph anyway. I just thought I'd mention that at the end. I didn't look at the time. That wasn't the quickest way of getting the answer for me. But anyway, I hope that's useful, and I hope that yeah, really helps you. Okay, all the best. Keep up the hard work, and bye bye.